Hello friends, today we are going to talk about motion in circle. Okay, now basically what are the types of motion that we know? The most basic is translational motion, then there is rotational motion and vibration or oscillatory motion. So what happens in translational motion? An object which is at point A, maybe point A here, it moves to point B here. Correct? So the coordinates of point coordinates of that object change. Initially maybe it was at x1 comma y1 and now it is at x2 comma y2. Correct? There is some linear displacement or some change in position. Okay, what about rotation? You can imagine motion of a ceiling fan. Okay, when we look at the fan, okay, it's running, but then you look at it, it is there. After 2 minutes you look at it, it is still there, but then there is some motion. That motion about an axis, that motion is rotational motion. What about oscillation or vibrational motion? Over there the motion is it is to and fro motion, like I can have a simple pendulum here, this bob hung from this rigid support, and I set it in oscillations. So what happens is it moves to this point here and then again it comes back to the mean position O, and again it will go to this position. Let us call this position P and position Q. So what is happening is O to P, P to O, O to Q and Q to O, and it repeats. Okay, so it is periodic motion, it repeats itself. Okay, but then it is to and fro motion. Okay, so at some point, at point P here, the direction of motion changes. Okay, it reverses. Okay, from Q, again from the Q, the other extreme, again the direction changes. So that is oscillatory motion or vibrational motion. Okay, but then circular motion or motion in circle is something different. I have this circle here. Okay, circle of, let us say, radius R, center is O and radius is R. Correct? My particle, maybe initially it is at point A here, then it will move like that. It will move along the circumference of this circle. Okay, and then in some time it will come back to A and it will continue and it will continue. Okay, so what happens is the motion is repetitive. Yes, I can say that it is repetitive because in certain time it moves from A along the circumference of the circle, it will come back to point A, again it will move to point B, then point C here, D, and finally come to point A, and it will continue. It will continue, it may continue, it may not, but then whenever the motion is along the circumference of a circle, it is called circular motion. Okay, now if the time taken from A to B to C and back to A, okay, if the speed along the circumference of the circle remains same, okay, or in other words we can say that particle moves along the circumference of a circle with uniform speed, correct, then it is called uniform circular motion. Now what is uniform speed? Speed is said to be uniform if the particle travels equal distances in equal intervals of time, correct, and then we call it uniform speed. So when a particle moves along the circumference of a circle with uniform speed, it is called uniform circular motion or UCM. Okay, now here in linear motion we have distance traveled or displacement is there, or then velocity is there, acceleration is there. Okay, now here, is there any displacement, is there any velocity, is there any acceleration? So everything is there, but then there has to be something different. Okay, my circular motion, it is translational motion because my particle is changing its coordinates during the course of motion. So it is translational motion, but then something different. This translational motion occurs along the circumference of a circle of certain radius. Okay, and then it is circular motion. So we have to define something over here. Let us see what all we have to define. So let us come back to linear motion. I am at point A and I move to point B. Okay, point A and point B. Okay, distance traveled is, let us say, S. S is the displacement, and then this displacement occurred in time t. Okay, so I can say my speed is equal to displacement upon time. Okay, this is average speed. We can say it is displacement upon time. Okay, but now what happens in circular motion? It looks like a circle, I believe. This is the center of the circle and this is my radius. Initial position is A. Okay, now since this is circular motion and it is happening in this direction, my particle at A would move to point B. Okay, now it is circular motion, right? So distance of my particle from O, initially it was r. Okay, now also it is r. At point B, distance is r. Okay, but the position has changed. Okay, the position has changed with respect to center of the circle. Okay, so for this purpose, we need to define this vector. Okay, OA bar or then OB bar. Okay, so what is OA bar and what is OB bar? OA bar and OB bar, they tell you the position of the particle on the circumference of the circle. This OA bar and OB bar, they are called position vectors or radius vectors. Now you must note one thing, magnitude of this radius vector, let us call it r1 bar, and magnitude of this radius vector r2 bar. Are they not same? They are the radii of the same circle. Okay, so I can say magnitude of r1 bar equal to magnitude of r2 bar, and that is equal to r. Okay, radius of circle, fine. But then what change did occur over here? Initially it was along OA and now it is along OB, isn't it? There is some change here, and that change is the angle that this position vector described with the center of the circle. Let us call this angle theta. Okay, this theta, this angle theta, it is called angular displacement. It is called angular displacement. Okay, now over here my displacement was S and it happened in time t, and then displacement, linear displacement upon time, we call linear velocity or linear speed, correct? Likewise, if my position changes, position vector changes from OA bar to OB bar, okay, that angle theta is described in, suppose let us suppose it is described in time t. Okay, time taken is t. T is equal to time taken. Okay, then I define my angular velocity as omega is equal to theta upon t. Okay, so angular velocity omega is theta upon t, correct? So it is simple. Now just as we have linear acceleration in linear motion, okay, or translational motion, we are going to have angular acceleration, and that angular acceleration, let us denote it by alpha, that would be equal to change in angular velocity per unit time. So it would be omega 2 minus omega 1 upon t. Now over here you would notice one thing, that if my particle is moving with uniform speed along the circumference of the circle, my angular velocity is going to remain constant, isn't it? So it will describe equal angles with the center of circle in equal intervals of time. So angular velocity would be constant. So in that case, would my angular velocity change, it is remaining constant, that means it is not changing. So in that case my alpha would be equal to 0. So for UCM, alpha would be equal to 0. Correct. Now as I said some time back, that this circular motion is a special case of translational motion. That means, there is going to be some distance traveled, okay, there is going to be some displacement, right, there is going to be some velocity, because since it has got some speed with which, in UCM, in uniform circular motion, this particle is traveling along the circumference of the circle with uniform speed. That means there has to be some velocity, there has to be some instantaneous velocity, isn't it? So when my particle is at point A, the direction of instantaneous velocity would be tangential to the circle. When it is at point B, then again I draw a tangent to the circle at point B. When it is here, again it would be tangential, and so on. Correct? The direction of instantaneous velocity is always tangential. Okay, but then even if it is uniform circular motion, okay, it has got instantaneous velocity which happens to be tangential, but then at every point of time, now here magnitude of velocity is v, okay, over here it is v, since it is uniform circular motion, over here it is v, and so on. But you must have noticed one thing, that the direction of velocity changes at each and every point, isn't it? So when do you say a vector is changing? A vector has got magnitude and direction, correct? So when either magnitude changes or direction changes or both of them change, okay, in that case we would say that a vector is changing, isn't it? So that means my velocity vector is changing at every point of time, and does it not mean that there has to be some acceleration? Yeah, because even though the magnitude of velocity is remaining same, my direction is changing, so that means my velocity vector is changing. So there has to be some acceleration, but then this acceleration, it is not changing the magnitude of velocity, but it is changing the direction of velocity. Correct? The point is, when this particle is over here, it wants to go in tangential direction, okay, but then there is something which pulls it back, and holds it onto the circular path over here, over here, over here, over here, over here, and so on. So the role of this acceleration would be to keep the particle moving along the circular path. The acceleration, okay, the acceleration which does this, okay, this acceleration is called centripetal acceleration. When we say centripetal, what does it mean? Centripetal means center seeking, okay, the acceleration which continuously pulls the particle towards the center of the circle, okay, it is only that you have to understand. Now let us try to figure out the relation between this angular velocity and linear velocity, angular speed, angular displacement and all that, right? Let us do that. All right, so first of all, let us have this circle, okay, and this is the center of the circle, and this r is the radius, okay. Now let us have the relation between this radius and this angle theta and length of this arc s. Okay, now what is the relation between arc length and radius? Okay, now here it is important that we define what is 1 radian angle. Okay, I'll tell you what is 1 radian angle. 1 radian angle is the angle subtended by an arc of length equal to radius of the circle at the center of the circle. 1 radian is the angle subtended by an arc of length equal to radius of the circle at the center of the circle. So what does it mean? When my S, arc length S, so if S is equal to R, if this arc length is equal to radius of the circle, then theta is equal to 1 radian. Now what is this C? That C is circular measure. Okay, this radian is circular measure of angle. Okay, so that is one relation. So then we arrive at this relation. So S is equal to R multiplied by theta when theta is in radian. Okay, all right. Now let us imagine that from point A to point B. Okay, what is the distance that I traveled? I traveled the distance equal to S. Okay, and that happened in time t. Okay, so if I divide this S, okay, by t, then that would be equal to R into theta upon t, isn't it? I am dividing both the sides by time. Okay, but then what is distance upon time? Is it not my velocity, linear speed? And so R, my radius is not changing, and the angular displacement divided by time, is it not our angular velocity? So this is the relation between velocity, radius and angular velocity, correct? So at any point of time, okay, the magnitude of velocity would be equal to the product of linear angular velocity and the radius of the circle. Okay, actually when we talk about velocity, okay, would it not be instantaneous velocity? Because velocity is a vector, right? So vector has to have direction, correct? So this velocity vector would be acting, you know, tangential over here, correct? So over there, so actually when I write something like this, I should be writing delta S, small arc would be equal to R multiplied by small theta, that is small theta, that is delta theta, and then delta S by delta t, small time interval again, so that would be R into delta theta upon delta t, and then that comes to the same expression here. Okay, now again if I have to find the acceleration, we all know, we have done that in calculus, that rate of change of displacement is velocity and rate of change of velocity, is it not acceleration? So if I divide this velocity by time, okay, again I'll be taking delta v by delta t, and over here again delta omega by delta t. So my delta v by delta t would be equal to R into delta omega by delta t. Okay, but then here this acceleration, okay, that would be equal to R multiplied by alpha. We denote this angular acceleration by alpha, but what if it is uniform circular motion? Okay, we need to find that out. So over here I am going to write V is equal to omega into R. Okay, now I will differentiate. So dV by dt, I am going to use product rule over here. So d omega by dt r bar. Okay, I am taking this vectors. Okay, I am taking vector forms. So dv bar by dt is d omega bar by dt cross r bar plus omega bar cross dr bar by dt. Now see, it is, now over here it is derivative of your radius vector or position vector, and that would give me the velocity. Okay, and d omega bar by dt, that would give me angular acceleration. So this would be alpha bar cross r bar plus omega bar cross v bar. Okay, Now here if you see, if it is uniform, if it is non-uniform circular motion, then my A bar would be equal to this alpha bar cross r bar plus omega bar cross v bar. So this is my tangential acceleration and this is my radial acceleration or centripetal acceleration, that is v omega. Correct. And this is the net acceleration. So it is vector sum, right? And radial and tangential. Radial and tangential are perpendicular to each other, isn't it? So the magnitude of my net acceleration, if I have to write, so A would be equal to, or magnitude of A bar would be equal to root over A tangential square plus A radial square. Correct? So again, coming back to our this expression, A is equal to V omega, okay, radial acceleration, I am calling it AR. But then what is my V? V, is it not R omega? So that would be R omega into omega, so that would be equal to omega square R, isn't it? Now instead of putting V is equal to R omega, if I put omega is equal to V upon R, so A would be equal to V omega, that is equal to V into V upon R, so that would be equal to V square upon R. Correct. So the magnitude of centripetal acceleration would be given by V omega or omega square R or V square upon R. In the next video we are going to talk about centripetal acceleration, centripetal force, and maybe there is something called centrifugal force, which happens to be a pseudo force, but then that we will be discussing in the next video. Thank you so much.